Hello everyone, welcome back to the Exam Tomorrow series, Lecture 3, Differential Equations. So in today's video, we are going to talk about linear differential equation and Bernoulli's differential equation, and then we are going to solve some respective problems. So without wasting any time, let us get started with linear differential equation. So we need to have a first order and first degree differential equation, and we want to arrange this differential equation in either this format or this format. So there are two possible formats for linear differential equation. Okay, first let us understand what is the meaning of the word linear. Well, we have already done this thing, linear, non-linear, in lecture 1 of this series. So a quick recap, what was linear? Linear is something, a term which doesn't have any higher power involved, or a term which does not involve transcendental functions like sine, trigonometry, sine, cosine, tan, then logarithmic functions, exponential functions, and so on. Okay, so any term which doesn't have higher power and transcendental functions are linear functions. So if I look at this differential equation, forget about the derivative portion. Let's say the derivative portion is invisible to us. Then what is the linear term we can see? The linear variable here is y. Okay, the linear variable is y because it only has a power of 1. Now you might say, well, p can contain some power of y, so that multiplied with the y will create a higher power. No, so we have restricted that p and q can only be functions of x. So for example, it might look something like this: dy dx plus x square y equals to sine x. Okay, so this is my p, which is x square. This is my q, which is sine x. So p and q are functions of x only. There is no y term involved. So what is the linear variable you can see in this differential equation? Let's say dy dx is invisible to us, the derivative term is invisible. Then the linear term is only y, which has a power of 1. X square is definitely non-linear, so that means x is non-linear over here, y is the only linear term. So that means we can say that such a differential equation is linear in y. Okay, so we say it's linear in y. That means the only linear term is y. Similarly, the differential equation might look like this. So if it is linear in x, then the derivative has to be of the form dx by dy and not dy by dx. So dx dy, px equals q. Now p and q has to be functions of y. So the only linear term present here is x. So that means we can say this is linear in x. Okay. So if the differential equation is either in this format or in that format, then their respective integrating factors are going to be e to the power integration p dx. Okay, whatever is the p, that p arises over here. Or if it is that case, then again same format, e to the power p dy, because now p is a function of y, so you have to integrate it with respect to y, where p is again something that arises with the x part. Okay. So this is the format. If we are able to arrange our differential equation in this format or that format, we directly get our integrating factors. The moment we get our integrating factor, we can multiply it both sides of the equation, and then we can solve it easily. Okay, so let's take a look at a problem. So first we need to bring this in the linear format. See, when I'm talking about linear format, your derivative term has to be free of any coefficient. The coefficient of the derivative term has to be strictly 1, right? The coefficient over here is 1, the coefficient over here is 1. So your derivative term has to have the coefficient 1 and nothing else. So we can see over here the derivative term has a coefficient of cos square x. So first we need to get rid of that. So if I divide by cos square x, so dy dx plus, if I divide by a cos square, so it becomes y sec square x equals tan x sec square x, right? So now if you look at this differential equation, you can see it is linear in y because y is the only linear term present. Rest all the terms are functions of x and they are in a non-linear format. So basically this differential equation is of the format dy dx plus py equals q, where your p is sec square x, your q is the entire right hand side. Okay, so we can say p is sec square x and q is tan x sec square x, and this is linear in y. So once it is linear in y, we can say that its integrating factor is going to be e to the power integration p dx, where p is sec square x, so integration sec square x dx, integration of sec square being tan x, so the integrating factor becomes e to the power tan x. That's our integrating factor. Okay, now we can remember that the solution also has a direct format. We can remember that format and apply it directly. That will save you time in your exam. Okay, once you have the differential equation in this format and you have got the integrating factor, you can say that if you multiply the integrating factor both sides of the differential equation that you have got. Now remember one thing, we are multiplying the integrating factor on both sides of the transformed differential equation, not the original one, the one which is in the format, required format. So basically if I multiply the integrating factor to this line, it becomes, I'll just write that line for once, e to the power tan x dy dx plus y e to the power tan x sec square x equals, my right hand side would become e to the power tan x into tan x sec square x. Okay, now you can remember one direct format of the solution. Okay, the format will always be d dx of y into integrating factor equals q into integrating factor. Okay, this will be the format of the solution. So that means I will be getting dy dx or ddx of y into integrating factor is e to the power tan x equals q into integrating factor. Well, I have already written that this is my q and this is my integrating factor. So q into integrating factor becomes e to the power tan x into tan x sec square x. Okay, now you might ask, how is this happening? How is this format coming? Well, if you observe this portion, if you do this derivative in the product rule format, ddx of product of two functions, if you do the derivative, you will see you will be getting these two terms. So it's just a back calculation. Okay, so this is what the integrating factor actually does. When you multiply the integrating factor, the left hand side becomes an exact differential. That means you can write it as derivative of some function. Okay, so basically derivative of that function is always of the format y into integrating factor. Okay, so if you do this derivative, you will get back to this particular line. So what we can do is directly remember this format of solution. Okay, so if I continue with this, so what I can do is I can integrate both sides. So it would become integration d of y e to the power tan x equals integration e to the power tan x into tan x sec square x dx. Okay, so this side would only be remaining as y e to the power tan x. On the right side we can do some substitution. Let's do the substitution. Tan x as z, so that means sec square x dx would be dz. So if I make the substitution, I will have e to the power z, tan x is z and sec square x dx is dz, right? So I need to do a product rule for integration over here, u into v formula. So that's going to be, if you have forgotten, I'll write the formula here, integration uv dx, or in this case it's dz. That's going to be u integration v dz minus integration derivative of u multiplied with integration v dz and then a whole dz, right? So if I use this formula, so over here I can say that my z is the u part and e to the power z is the v part, right? So if I do this integration, I will be having u into integration of v dz. So integration of e to the power z will be e to the power z again, minus derivative of u would be, that means derivative of z will be 1 into integration of e to the power z, that will be e to the power z dz. So we'll be having z e to the power z minus e to the power z. So e to the power z will again mean e to the power tan x. So if I take the e to the power tan x common, I'll be having z minus 1, and z is tan x, so that's tan x minus 1, and on the left hand side I have y e to the power tan x. So what I can do is just divide by an e to the power tan x. Acha, one more thing, I should write an integrating constant over here, plus c, so an integrating constant should be present. So now if I divide by e to the power tan x, I have y e to the power tan x getting cancelled, tan x minus 1, but don't forget to associate or divide c with e to the power tan x. So e to the power tan x should be associated with the constant, so plus c e to the power minus tan x, because I'm dividing by a e to the power tan x. So I can say this is my final answer to the linear differential equation. Okay, so now what I will do, I'll just go back to this slide and I will just mention the format of the solution after multiplying the integrating factor. If you remember, the format for solution after multiplying the integrating factor was y into ddx of y into integrating factor equals to q into integrating factor, right? So we had used this format of solution. For that case, the format of solution would be ddy of, okay, because here it was ddx, here it's ddy, so ddy of, here I had y into integrating factor, in this case I will have x into integrating factor equals q into integrating factor. Okay, so these are the two solution formats that we can use for the two different linear equations. Okay, so let's move on to question number 2. Now, first we need to look at the question and decide whether it is linear in x or linear in y. So how to understand that? If you look at this differential equation, let's suppose the derivative term is invisible to you. Okay, let's suppose the derivative term is invisible to you. Now the question is, what is the linear variable you can observe over here? Definitely y is not linear because higher power of y is present. Y to the power 2 is present, so it's a higher power, that means not linear. 1 by, if you see 1 by y, that is again reciprocal of y, so reciprocal is again non-linear, it's not linear. So that means y is not linear in format. Here x is in linear format because it has a power of 1. Okay, so that means by looking at this differential equation, you can understand that this is linear in x. Okay, this is linear in x. So the moment you have understood it is linear in x, you need to recollect that its general format is dx dy plus px equals q, where p and q must be functions of y, right? So I need to bring it in that format. So now I need to express, sorry, I have written this wrong, dx dy. So I have to bring it in the format dx dy. Here I have dy dx, that means I need to reciprocal the things which are present over here. So I'll just arrange it in that format. So I have x minus 1 upon y dy dx. I'll take the y square that side equals minus y square. Now I can just make cross multiply things over here. So if I cross multiply, x minus 1 by y equals to minus y square dx dy. So I have got my dx dy format. Now I just need to arrange it in this style. Okay, my dx dy should strictly have a coefficient of 1. Here dx dy has a coefficient of minus y square. So that means I need to divide by a minus y square. So dx dy, I am dividing by minus y square on both sides. So I'll have minus x by y square plus 1 by y cube. Okay, I have divided by a y square on both sides, minus 1 by minus y square on both sides. Okay, now I'll just bring one of the terms to the left side to match it with the format. So it's going to be dx dy plus x into 1 by y square equals 1 by y cube. So I have basically brought this term on the left side. So you can see this is of the format dx dy plus px equals q. So your 1 by y square is your p, 1 by y cube is your q, which are functions of y only. So that means it has been arranged in the format linear in x. So you can say that its integrating factor is going to be e to the power integration p dy, right? So p is 1 by y square dy. If you integrate this, you are going to get e to the power minus 1 by y. So that is your integrating factor. So now we are going to use the direct format of the solution. So one line you have to write, it's mandatory, otherwise your marks might get deducted from the exam, that multiplying the integrating factor both sides of this particular equation. So if I multiply it on both sides, I'll just write that line as a mandatory statement for your exams. So multiplying by the integrating factor would make it e to the power minus 1 by y dx dy plus e to the power minus 1 by y x by y square equals e to the power minus 1 by y cube. So I've multiplied it. Okay, now I'll directly go to the format of the solution. The format of the solution was d dy x into integrating factor equals q into integrating factor. So that would be d dy of x into integrating factor is e to the power minus y, and q into integrating factor is basically, this is your q into integrating factor, right? Because I've already multiplied. So q into integrating factor is 1 upon y cube e to the power minus 1 by y. Okay, so now if I integrate both sides, I'll have x e to the power minus 1 by y equals integration 1 by y cube e to the power minus 1 by y dy, right? And to do some substitution for this, let's see what we can do. Let's substitute 1 by y equals z, right? So that would mean minus 1 by y square dy equals dz. Let me get rid of the minus sign. So 1 by y square dy equals minus of dz. Let's try to plug this in over here. Okay, so to plug that in, we need to do a little bit of adjustment. I can write this as 1 by y e to the power minus 1 by y into 1 by y square dy. So I have split the 1 by y cube as 1 by y and 1 by y square. Okay, so your 1 by y square dy, that's going to become minus dz, and rest I will get from the substitution of z, right? So 1 by y is simply z e to the power minus z, and this becomes dz. So again, a similar kind of by parts we can do like the previous question. So I'll directly do the by parts now. So you can understand, this is your u function, this is your v function. So if I do the by parts, I'll have z e to the power minus e to the power minus z plus integration e to the power minus z dz. So that would be minus e to the power minus z common, z plus 1. So that's the integration that we are getting. So I'll plug back the z value over here, and on the right side I have x e to the power minus 1 by y. On the right side, in place of z, I need to plug back 1 by y value. So if I do that, minus e to the power minus 1 by y, 1 by y plus 1, and definitely there has to be an integrating constant plus c. So an integrating constant plus c. So what I can do is I can get rid of the e to the power minus 1 by y on from both sides. So if I divide by e to the power minus 1 by y, I'll have x minus 1 by y plus 1 plus c e to the power 1 by y, because basically I've multiplied with the e to the power 1 by y both sides, right? So this is our final answer to the differential equation, right? So I hope you understand how we are solving linear differential equations. Now moving on to Bernoulli's differential equation is just an extension of linear differential equation. So Bernoulli's differential equation, it's again first order, first degree differential equation. And again, there are two formats of Bernoulli's differential equation. Okay, The difference with the linear and Bernoulli is that the presence of y to the power n on the right side in the first case, and in the other case the presence of x to the power n on the right side. Rest you can see everything is same as before, right? This part is same as linear in y and this is same as linear in x. Okay, so it's almost linear in y but multiplied with a y to the power higher power on the right side. This is almost linear in x but multiplied with a x to the power higher power, right? So now these are not linear anymore because p and q are any functions of x. So any functions of x means it is free to become non-linear. So we can consider that x is non-linear in general and y higher power is present, so that means it is not linear in y also. So basically a Bernoulli differential equation is not a linear differential equation, it's definitely non-linear. Okay, so now the process is this higher power, this unnecessary term on the right side which is creating the non-linearity, creating the problem, we need to divide by that term. Okay, we have y to the power n, we need to divide it by y to the power n. In this case we need to divide by x to the power n both sides. So first we need to bring this format or that format, divide by that unnecessary term. Once the division is done, we need to make a suitable substitution. Okay, now what that substitution will be, I will explain to you while doing a problem. Okay, I don't want to generalize it. We will substitute something. Once the substitution is done, this differential equation will now look like a linear differential equation. Okay, so it's going to become linear. Once you substitute, it's going to become linear. In that case also, once you substitute, it becomes linear. The moment it becomes linear, you already know how to solve it. In the previous questions, you have done that. Okay, so this is the total outline of how the thing is going to work. Now remember one more very important thing I'm telling you. It's not mandatory that always this term will be y to the power something. It may be some random function of y also. For example, log y whole square, tan y, sin y, trigonometric terms. Okay, similarly this term, it always need not be x to the power something. It can be some non-linear term of x also. Then also this entire process is going to work. It's not fixed that it has to be a higher power of y or a higher power of x. It can be some other non-linear term also. Then also this same process will work for it. We will do that kind of sum right at the end. Okay, so first let's do this question. We need to bring it in the Bernoulli equation format first. So format means your derivative term has to be free of any coefficient. That's the very first thing you need to keep in mind. So over here you can see your derivative term has a coefficient x. So you need to get rid of that. So that means basically you need to divide by x first. So very first thing I'll do is divide by x. So dy dx plus y by x equals xy square. So you can see, or I'll write it in a little bit better way, dy dx y into 1 upon x equals to xy square. So you can see this portion is your linear in y and one higher power of y is multiplied. Okay, dy dx plus py equals q multiplied with y to the power n. So it's basically this format which is present. Okay, so we can say that this is our p 1 by x, this is our q, and this is the y to the power n. So it's directly matching with the format. Now as I told you, first step is once you have brought the format, divide all over by the term y to the power n. That means divide by y square all over. That's step number 1. So we'll divide by a y square all over. So I'll have 1 by y square dy dx plus 1 by xy equals x. Okay, now what did I tell? We have to make some substitution. Okay, what will be the substitution? See, the easiest way to remember this, focus on the middlemost term. Okay, middlemost term means always we are having 3 terms, right? This is the first term, this is the second term, this is the third term. Okay, so always in a Bernoulli differential equation we are having 3 terms. Focus on the middle term. In the middle term, except x. Suppose x is invisible to you. If x is invisible to you, then what can you see? You can see 1 upon y. So just remember, if x becomes invisible to you, whatever x term is there, if that becomes invisible to you, then whatever remains, just substitute that as z, and the equation will become linear in z. Okay, let's see how that happens. So if I do the derivative over here, so I want to do the derivative of this substitution with respect to x. So derivative of 1 by y is minus 1 by y square, but I am doing the derivative with respect to x, so I need to have dy dx equals, right side also I am doing the derivative with respect to x, so dz dx. Now the interesting thing is that if I just get rid of the minus sign, okay, if I get rid of this minus sign, so 1 by y square dy dx is equals minus dz dx, you can see this term is present right over here. Okay, so the first term is now going to become minus dz dx. So now I'm going to plug in the substitution. Okay, so if I plug in the substitution, this first block term becomes minus dz dx plus 1 by y I have substituted as z. Keep the x as it is, don't tamper with the x term. 1 by y is z, so basically I have z by x. So I have z by x. Right side x is going to remain as x. Okay, now if you observe, this has become linear in z. Okay, the only linear term is z, but remember that you will call this linear in z once the coefficient of the derivative is strictly 1. Okay, here the coefficient is minus 1. So let's get rid of the minus sign. So dz dx plus z into minus 1 by x equals minus x. So I've multiplied with a minus term. Now you can see this is of the format dz dx plus pz equals q. So your p is this term and q is this term, and this you can say it's linear in z. Right? So the substitution has made the Bernoulli's equation a linear differential equation. Now we already know how to solve a linear differential equation. What we can do is we need to find the integrating factor. That's going to be e to the power integration p, and p is a function of x, so p dx. So e to the power integration minus 1 by x dx, and that's going to become minus log x, right? E to the power minus log x, so that's going to become simply 1 upon x. So this is our integrating factor. Now again we're just going to multiply the integrating factor on both sides. So on the both sides of the differential equation, if I multiply the integrating factor, 1 by x dz dx plus z minus 1 by x square equals minus 1. Now we know the solution format of this, so we can write the solution format is going to be d dx of, instead of y here we have z, right? Instead of y we have z. So previously it was y into integrating factor, so now it's going to be z into integrating factor, which is 1 by x, equals to, right hand side is going to be q into integrating factor. What is q into integrating factor? We have already got that. Our q was minus x into integrating factor. We have already got that as minus 1. So q into integrating factor is minus 1, right? So this was the solution format. So if I integrate both sides, z by x equals minus integration dx. Right? What was z we had substituted? Z was 1 upon y, right? Z was 1 upon y. So if I plug that back here, so z is 1 upon y, so 1 by xy equals minus x plus integrating constant c, and this is the answer to our Bernoulli's differential equation. So it's quite simple. I hope you are understanding the concept. So let's do one more sum. So this is another question. Now you can see the derivative is in dx dy format, not the usual one, the second format. So first of all, we need to check whether it is in the perfect format or not. So if I just bring the y square and interchange the y square and x square, that means if I write it this way, dx dy minus 2xy equals y cube x square, then this much portion I can say, if I consider this much portion, then it's linear in x multiplied with a higher power of x, right? So that means it's perfectly in the Bernoulli format, that second format. So first of all, you need to start by dividing by the higher power of x. So you need to divide by x square first. So dividing by x square, dx dy minus 2y by x equals y cube, right? So in the previous sum, I told you that if x is invisible, then whatever is remaining, you substitute that. In this case, the reverse thing I'll be saying, that if y is invisible to you, whatever else is remaining, that should be a substitution. So if your y is invisible, what is remaining? 2 upon x. So this you can substitute. Now, some important things to be concerned over here, that is, you might want to consider the negative sign, you might not want to consider the negative sign, no problem with that. Okay, one more thing, you might want to take the 2 or you might not want to take the 2. Okay, that means you can take 1 by x as your substitution and keep the 2 as it is, or you can include the 2 in your substitution. It won't affect the final answer. Okay, it won't affect the substitution at all. You can either include the constants or exclude the constants from your substitution. It's advisable to exclude the constant. It makes your further calculations more simpler. Okay, so I am going to exclude the constant. I'm going to take 1 by x as z. Okay, so if I do this derivative with respect to y, because over here you can see the derivative is with respect to y. So to do the derivative with respect to y, it will be minus 1 upon x square dx dy equals dz dy, right? So I need to get rid of the minus sign. So now you can understand that if I had considered this minus sign in my substitution, then this minus wouldn't have been there. It would have been a little more easier. Okay, so these things you can keep in your mind, or if you're doing for the first time, don't worry, the terms will get self-adjusted. Okay, so if I get rid of the minus from here, I get something like this. Now I can put this value from the substitution, right? So minus 1 upon x square dx dy, that's going to become minus dz dy, minus 1 upon x, that's going to become z, so yz equals y cube. So I need to get rid of this minus sign from the derivative coefficient. So dz dy plus yz equals minus y cube. So now we can say this is linear in z, right? Z is the only linear term you can see over here. So now again, direct solving process. Okay, so I can say the solution format. So I'm not multiplying both sides by the integrating factor and all that. I'll be directly jumping to the solution. I'll just find the integrating factor and jump to the solution. So integrating factor is going to be e to the power integration. This is my p term, so p dy. So that means e to the power y square is my integration. E to the power y square by 2, that's my integrating factor, right? So if I multiply by the integrating factor directly, the solution format was d dy z into integrating factor equals q into integrating factor, right? This was the solution format. So now if I integrate this both sides, z e to the power y square upon 2 equals integration y cube e to the power y square upon 2 dy, right? Again, I need to do some substitution over here to make it simple. So I can take y square upon 2 as, let's say, p. So that would be y dy equals dp. So I can break this y cube as y square e to the power y square upon 2 into y dy. So I've broken the y cube as y square and y. So this portion y dy is going to come from our substitution. So if I do that substitution, I have y square. From here I can say y square is 2p, right? Y square is 2p. So it is a y square, I can write 2p e to the power p, and this is dp. So again, a simple by parts over here, minus 2 goes common. The by parts of this we have already done in the first question. So that is actually e to the power p goes constant, and we get p minus 1 plus integrating constant c. On the left side we have z e to the power y square upon 2. Now we need to substitute back all the variables. Okay, this is where people forget. They leave the answer here, marks will get deducted. You need to substitute back everything. Okay, what was z? Z was 1 upon x, right? Z was 1 upon x. So first let's bring back z. So z is 1 upon x e to the power y square upon 2 equals, coming to p, what was p? P is y square by 2, right? P is y square by 2. So minus 2 e to the power y square by 2. Y square by 2 minus 1 plus integrating constant. So let's get rid of the e to the power y square by 2. So I'll have 1 by x equals minus 2 y square by 2 minus 1 plus c into e to the power minus y square by 2, and that's our final answer, right? So I hope this is making sense to you now. Now I'll do one more last question, but this question will not match with the Bernoulli format. As I told you, sometimes the Bernoulli, the nonlinear term of Bernoulli might not be of the format y to the power n or x to the power n. It might be some other term. So that kind of sum, let's take a look. So this is the question. So over here we can see that first of all the derivative has a coefficient of 1. So that's not a problem. That's a very good thing. Now you need to understand what do we divide both sides with, because this is not directly in our Bernoulli format. Okay, so what we can do is, see, observe one thing. Whenever I am dividing in the first line, whenever I am dividing by the higher power, I am making sure that my right hand side only has one variable, right? In this case, after division, the right hand side only had one variable, which was y. In the previous problem of this one, we had a higher power of y square. Upon division with y square, the variable remaining on the right side was x. So always after division on the right side, we were maintaining one variable. So let's try to do something like that over here also. So let us divide the entire equation with y log y square, such that after division we are only left with the x variable on the right side. Let's free the right side from the y variable. Okay, so that means after division we are going to get 1 by y log y whole square dy dx plus, if I divide by y, so this y is getting cancelled, dividing by log y whole square, so one of the log y is also getting cancelled, so I'm left with x log y equals, right side is 1 upon x square. Okay, now let's suppose x is again invisible to you. So if x is invisible, what is remaining? 1 by log y. So this is what you are going to substitute. So always remember, you're going to substitute something like that, which upon derivative will create your first term. Okay, this is the back calculation you need to think of. So if I do the derivative of 1 by log y with respect to x, I will end up creating the first term. So that's our objective. Okay, so if I substitute 1 by log y equals z, so if I differentiate this, I will have, first of all, 1 by log y derivative is going to be minus 1 by log y whole square, followed by chain rule, derivative of log y will be 1 by y. We are doing the derivative with respect to x, so followed by a dy dx equals dz dx. So if I get rid of the minus sign, I have created the first term. So that means 1 by y log y whole square dy dx is equals minus dz dx. So I have created the first term right over here, right? So if I substitute it, I'm going to get a minus dz dx plus 1 by log y is z, so z by x equals 1 by x square, right? Let me get rid of this minus sign, so dz dx minus z by x equals minus 1 by x square, and I can say that this is linear in z, right? So I'll jump to the integrating factor. The integrating factor is going to be e to the power integration p dx. What is my p over here? My p is minus 1 upon x, right? So minus 1 upon x dx. So that's going to be, so don't forget to take the minus sign. People make the mistake over here. You need to include the minus sign, okay? So e to the power minus log x, and that's going to be 1 upon x. That's our integrating factor. So now I am jumping to our solution format. So that's d dx of z into integrating factor, which is 1 by x. Right hand side, q into integrating factor. Q is minus 1 by x square into integrating factor 1 by x, right? So now integrating this both sides, z upon x equals minus integration 1 upon x cube dx. So that's again a very simple integration. So z upon x minus minus, that's going to become plus. So it's going to become 1 upon 2x square plus integrating constant. Now what was our z? Don't forget to substitute it back. Z was 1 upon log y. So if I bring it back, so 1 upon x log y equals 1 upon 2x square plus c, and this is the final answer to the Bernoulli's differential equation. So I hope this video makes sense to you. So in our next video, we are going to solve first order but higher degree differential equation. Up till now we are doing first order, first degree. Next is going to be first order but degree higher. Okay. So again, that is going to have some categories. So we'll look into that in our next video. See you there. Thank you for watching.